Chao Wang. Chao, okay, I see you here. You want to go ahead and project your screen?
Yes.
Okay, great. I see your slides. All right, so it's my pleasure to introduce Professor Chao Wang at the University of Southern California. Chao is an associate professor at USC, and he's worked extensively on many topics in software engineering, formal methods, and related areas. He has published 2 books and many papers, and many of them have been recognized with paper awards. And he's received the Early Career Award for the NSF from ONR and a distinguished dissertation award. So, Chao has been doing some very exciting work on synthesis and its applications, and eager to hear about this today.
Can you hear me now?
Yes, we can hear you.
Okay. First, thanks for the invitation, and I'm happy to talk about our work on side channel analysis. First, I want to acknowledge my collaborators over the years, especially Jing Bo, who is currently a PhD student at USC, and she is the driving force behind this work. Today, I'm going to first briefly explaining what side channel analysis is, and then I'll talk about a specific type called power side channel. And then after that, I will talk about a few key ideas behind our method, and finally, I'll show the evaluation results. I think most people heard about side channel in 2018 after the Meltdown and Spectre attacks were revealed. So these are the attacks that affected many microprocessors in both personal computers and also data centers. And the main thing behind this is cache timing side channel. It's due to a hardware level optimization called a speculative execution. But this is only one example of the many possible side channels. There are more. And if you look at here, besides timing, there can be sound, heat, EM emission, power, and even injected faults. They all can be used as a side channels. So today's talk, I'm going to be focusing on one type called power side channel. But in this context, a static analyzer is a software tool that, for a given program and a leakage model, try to decide whether it has a side channel leaks. Here, the leaks are really statistical dependencies between the secret data and the what you can observe from the side channel. And like any static analyzer, when you try to design one, you face the trade-off among soundness, completeness, and termination, or practically fast. So in this context, we choose soundness and termination. And this is reasonable for security applications. For example, if you are not sure whether a software code, a piece of software code is vulnerable or not, you don't want to say that it's not vulnerable. And then the next question is, how do you design such a analyzer? So there are 2 options. You can manually craft it, or you can use data-driven synthesis. There are disadvantages of manually crafting such analyzer. It's labor-intensive, error-prone, and it can be suboptimal. And also, once you design the analyzer, it's hard to adapt to the changing characteristics of the target program. But if you use data-driven synthesis, you can avoid all these problems. So next, I will use a few examples to explain the nature of power side channel. So I want to start with the classic example, which is a smart card running an encryption algorithm. So here you can see the bit streams coming in. These are the plain text. And then the bit streams going out. These are the ciphertext. There is also a chip-specific crypto key here. And you want to keep it secret, because otherwise encryption is not going to be very useful. But if you are able to observe the fluctuations of the power consumption where you're running the encryption algorithm, then it might be fairly easily for you to deduce some sensitive information about the key. And that's called side channel attack. So there are well-known techniques for doing that. For power set channel, there is this differential power analysis. And like here, if you put a current sensor between the power supply and the computing device, so this is the embedded computing hardware running some cryptographic software, then you can measure the power consumption over time and using an oscilloscope, and then you can collect many of them and then put it into a PC, and then you try to do some kind of statistic analysis. And if the secret data are not protected even by countermeasures, this might be fairly easy, right? You can directly see the sensitive data from this kind of a power measurement trace or the power fingerprints. So that's why countermeasures are widely used in this context. And for power set channel, the most popular one is called masking. And you're using some random bit strings to try to break the statistical dependencies between the secret data and what you can observe from the power set channel. So in this slides, I want to use a few examples to try to illustrate at a high level what this masking is doing. So let's assume that you have a leaky computation. There's a Boolean function fx, and you don't want the sensitive input x to be leaked through this yellow box. What you can do is to take a random bit, try to use XOR to randomize the input before you fit it into this leaky computation. So whatever that is going to be leaked through this yellow box is randomized. So if someone has to aggregate it over time, they will get white noise. But then you also want to recover the C, right? So then you take the same bit string, you fit into the same function f, you get fr. And then you XOR this with the output, you would recover this. This is very nice, but it only works if f is a linear function, linear in terms of the XOR operator. But real-world cryptographic software, they all have nonlinear components, so you really cannot do that in any straightforward fashion. So you would have to ask a domain expert to try to rewrite this entire program to bake the countermeasure in from the ground up. But even after that, you have no idea if the software code is implemented correctly. So there is verification needed here. So here I'm trying to use this small example to illustrate what the side channel is, right? It's the statistical dependencies between the secret bit and what you can observe through the side channel. So here the chi function has one of the input, the secret bit, I1. And if you can observe something related to the value of N1, the question is, can you infer something from N1 about the value of I1? So for that, we can build a truth table. And here in this truth table, I1 is one of the input columns and N1 is one of the output columns. And you notice if I1 has value 0, out of the 4 rows, one of them, N1 has logic 1. But if I1 is 1, then 3 out of the 4 cases, N1 is 1. So if we know that in a CMOS device, in a circuit, the logical 1 consume a little bit static current than logic 0, then by observing the output, you might be able to infer something about the input, the secret bit. So that's a side channel. Now, in order to mask it, you can rewrite the program. And here you're using some random bit strings to try to randomize the sensitive bit before using it in this leaky computation. Now, here you can see that N1 seems to be logically dependent on this random bit, right? First of all, it's syntactically dependent. And second of all, it's if you look at harder, you would realize that it's also logically dependent. It's semantically dependent on this random bit. So it seems that it has been masked, but still you don't know whether the mask is perfect or not. So the real question here is, after the masking, do we know whether N1 is now statistically independent from the secret bit I1? So that's the verification problem. And you can imagine that conceptually you could build a huge truth table, right? This is going to be of size exponential, right? And then start counting the number of ones in the first half, the second half. but this will be not practical. So that's really the verification problem. Now we're ready to talk about our method for automatically synthesizing static analyzer to solve the verification problem.
Chao,
Yeah.
just one minor point. There seems to be some noise coming from your end, perhaps an open window or something. I wonder if, yeah, that helps a lot. Thank you.
Is it better now?
Yeah, much better. Thanks.
Okay. Thank you. So our method starts with some kind of a training data. So here the training data are programs and type annotations. These type annotations indicate whether the corresponding programs have leaks or not. And then we have two components. One is the learner and the other is the prover. The learner is responsible for generating analysis rules from the training data. And then the prover is responsible for proving them. And only the proved rules will be added to the learn analyzer. And in that sense, we can guarantee that the learn analyzer is going to be provably sound. And all the rejected rules will produce counterexamples, which will be added back to the training data. And so in the future, we won't see the same rules generated again. So now let's look into the learner. The learner would have two interacting components. One is for synthesizing the analysis rules, and the other is for synthesizing the features. For the rule synthesis, we're using decision tree learning, and for the feature synthesis, we're using syntax-guided synthesis. So I'm going to explain in the next few slides why we make such choices. So now let's look at two concrete examples. So from the training data, we can extract some abstract syntax trees. These are representing the intermediate computation results of the program. And the type annotation start with the input. So we can label the inputs. Here, UKD stands for unknown, means that we're not sure if this one is leaky or not. So let's just assume it's not secure, it's leaky. And then this in rand means it's an input bit and it's a random input bit. And once we have the lower level labels, we can start labeling the remaining nodes. So here B2 will be labeled RUD, means random uniform distribution, means that it has been perfectly masked, it's considered secure. And the reason is because one of its operands, R2, is actually the input bit, and it's randomized, and this is exclusive OR, so whatever the other operand is, this is perfectly masked. So similarly, we can label the other nodes. And this thought process can be codified as an analysis rule. And this rule basically says, well, look at B2, if the left operand is UKD, the right operand is in rand, and the operation is exclusive OR, then this is perfectly masked. And this may sound trivial, but I'm using it here to just give you an idea of what this kind of analysis will look like. Now we try to label the top level nodes. Here, N1 is actually UKD. Although both of its children are perfectly masked, they're actually masked by the same random bit. So at the top level, the masking is going to be removed accidentally. But for the other node, it remains RUD because the two children are using two different random bits for the masking. And the difference between these two ASTs can be codified by another analysis rule. And this rule is a little bit more complex because it's using some recursive relations like DOM here. But essentially it says, a AST tree has to be looking more like the right-hand side in order to be labeled RUD. Here, DOM means, the left child must be recursively dependent on some random bit RL, and the right-hand side child has to be recursively dependent on some random bit RR, and RL and RR are different. So by now, hopefully, it's clear that we need to learn two things. One is a set of features, and the other is the set of rules. The features are really the predicates that are used in these rules. They can be the distribution types, the unary operators, the binary operators, and also this kind of recursive relations. The rules are really the sufficient conditions for a certain node to be of a certain distribution type. If you're familiar with data log, you'd see these are essentially data log rules. If you're familiar with horn clauses, these are the first order logic horn clauses. So for learning the rules, we're using decision tree learning. And the reason is because if you look at a decision tree like this, you would see that path in the tree naturally correspond to some sufficient conditions for a certain program variable to have a certain distribution type like RUD. And so each tree captures a set of analysis rules in our case. If we apply this decision tree to some concrete program, then we can label, we can classify for each program its distribution type. So this is all very nice, but there are sometimes the current set of features you have to construct the decision tree may not be expressive enough. That's when you would observe some path like this red path, where at the bottom there are these two nodes, B4 and N1. According to the ground truth, they should have different labels, but because we don't have enough features for constructing this tree, we're not able to separate them. So this is when we would know that we need more features. So that's why this feature synthesis is going to be invoked on demand whenever this tree has ambiguity. And so this is basically syntax-guided synthesis from a certain grammar. We would be able to construct the new feature. And this new feature has to be able to reduce the ambiguity of this tree. In the context of decision tree learning, so this new feature, when it's added, is supposed to be able to increase the information gain along this kind of a red path. So if we keep doing that, all these ambiguities in the current decision tree will be eventually removed. And we would have a decision tree that is fully consistent with all the training examples. So the ground truth. So that's when we are ready to move on to the prover. Here we need to ask this question. Are the learned rules sound, not just for the training programs, but also for all the other unseen programs for which you might want to apply this analyzer? And this, as you can imagine, is a challenging problem because the set of unknown programs is infinite. So unlike the training programs, you cannot enumerate them and then try to validate the rule on each of them. So instead, you need to think about this as a query containment checking problem. So here you can assume that this learned rule alpha is a data log query. And we also need to build a proof system, which we call the knowledge base. And it also can be expressed as a data log query. Now you have two data log queries. You want to prove that one query is contained in another. So in terms of the query language containment. So that's one way to understand this prover. Another way to understand the prover is to think of the alpha as a first order logic formula and KB as another first order logic formula. And both are represented in the form of horn clauses. Now the question is, how do we prove that alpha entails KB? Now, whichever way we take, the prover needs to be able to produce two possible outcomes. One is that the learned rule is proved to be sound, in which case it will be added to the learner, to the analyzer. Or if it fails to prove it, it will just produce some abstract counterexamples that will be added back to the training data set. So the knowledge base is a set of proof rules that are known to be correct. So in this work, we have two sets of proof rules. One is for propositional logic. The other is for the distribution types. We know that for propositional logic, there are sound and complete proof rules. So these rules are just taken from textbook. For the distribution types, these are rules collected from prior publications on formally verifying masking countermeasures And these are the rules that have been proved to be sound. So we're just taking it and use it here. Now we have two set of queries, the alpha and the KB. We're ready to decide the query containment. I want to make two key points here. First, data log query containment checking is known to be undecidable in general. But in practice, there are decidable fragments. And for our context, all the rules that we see in practice are in this decidable fragment. But our synthesis framework actually doesn't really need the procedure to be fully decidable, right? We only need it to be semi-decidable. So here's what I mean. If you imagine that KB and alpha as queries, so the queries would return some results, right? These are the set of programs for which the labels are consistent with the queries. Now we can imagine the entire universe as all the possible programs that you might want to apply your analyzer. KB defines a subset. These are the secure regions. And as long as alpha, the subset is defined by alpha, falls within this secure region, then we know that alpha is sound. So in the actual implementation, we're proving alpha entails KB using SMT solver together with K induction. So I'm not going to go into the details, but the high level, it's analogous to unbounded model checking, where you just keep unwinding, unrolling the recursive formulas inside the data log programs of both alpha and KB, and then you try to justify that alpha always entails KB. So it's like any induction proof. We just first assume that this entailment holds for all the k-1 steps. And based on that, we try to show that it should also hold for the kth step. So now we're ready to look at the evaluation results. In the evaluation, we want to ask two questions. First, is the synthesized analyzer fast enough and accurate enough when it's compared with the state-of-the-art handcrafted analyzers? The second question is whether the synthesis is really effective. There is a learner, there's a prover. Is the learner learning the useful analysis rules? And is the prover able to prove them? The benchmarks we use are C programs that are implementing cryptographic algorithms. So we have the training set. Training set has 531 small programs. These are the code snippets annotated with the ground truth. We also have the test set. These are the 37 larger programs taken from prior publications where they were used for benchmarking. So overall, we see that the synthesized analyzer achieved almost the same empirical accuracy as the existing analyzer. There are 37 test programs. Out of 37, on 33 of them, the results are the same. So there is no difference in the analysis results. On only 4 of them, we see differences. So out of these 4, these are the 3 where our learned analyzer doesn't perform as well. It reported more UKD, the unknown types. And on 1 of them, our learned analyzer does a little bit better. It reported fewer unknown cases. But overall, the empirical accuracy are almost the same. And the real difference is in the execution time. We will look at the execution time, we find that our learned analyzer is much faster than the existing analyzers. For the most recent ones, we are more than 200 times faster. For the older ones, we are more than 900 times faster. And here are the results on the synthesis procedure. So the synthesis procedure is reasonably fast. So it took 30 iterations where each iteration is a repeated evocation of the learner and then the prover for constructing different type of decision trees. And each iteration took like 1 or 2 seconds. Here, the x-axis are the 30 iterations, the y-axis are the execution time in seconds. These are more statistics on the learner and the prover. Along the axis, again, these are the 30 iterations, y-axis showing the number of synthesized features, the rules learned, the rules verified, and also the number of abstract counterexample added back to the training data set. So as you can see that as the number of iteration increases, we're learning more and more features, and the learned rules are, most of them are proved, and it seems to be doing what we were expecting it to do. So our conclusion is that through this work, we found that data-driven synthesis seems to be a good idea, at least in practice for synthesizing a side channel analyzer. It's fully automated and it's provably sound. And we're now thinking about applying similar ideas to other side channels. And as I mentioned at the beginning of this talk, there are many other side channels. They're all very exciting. At a higher level, you can see that a side channel verification tool is only a part of the story, right? It's for either detecting vulnerabilities or verifying that there is no vulnerability. But there are also these related questions. One is automated synthesis of countermeasures, and the other is if you are given an existing implementation, you might want to quantify. You might want to quantify the amount of information leakage. For example, using notions like Shannon entropy or mean entropy. So overall, this is a nice application of automated, formal analysis or program synthesis. So we've done some work in the past along some of this direction. So if you're interested, I listed some of these related papers on this topic. So that's all what I want to say. I wonder if there are questions.
Thank you, Chao. That's a very interesting results, and I would say a very innovative use of synthesis. Are there any questions from the audience? Okay, I had a couple of questions. Let me start off with that. I wondered, in your use of Cygus, did you have any thoughts on where current Cygus technology falls short for this particular applications? Like what sort of things you feel would be useful to have in Cygus solvers to be able to push the boundaries for this particular class of synthesis problems?
For our application, we think it's working fine because we're only using it to synthesizing these features. These are only the predicates. And then when we try to use these features to try to piece together the analysis rules, we're using decision tree learning. And the reason is because the decision tree learning is more scalable. And in theory, you can imagine, well, why don't you synthesize the whole rule using Cygus? You can. There is no reason you cannot. But if you think about it along the same way, then why don't you just replace decision tree learning everywhere with Cygus, right? You can also do that in practice, but probably in that case, you cannot construct a decision tree that is bigger than 4 levels, right? We saw existing papers where some people actually do that in operational research, right? So mixed integer linear programming, where they try that, and beyond 4 levels, it might be very hard. It would just run for several hours.
Right. Okay. And then I had another question about one of the graphs in your results. So when you had these 4 plots on one slide, and you showed the number of verified rules right here, right, bottom left. So this fluctuates, and I'm trying to understand what the reason it fluctuates is because one of the new counterexamples you get refutes number of rules, and so you have fewer verified rules. So what is going on there?
So these rules are they are all consistent with the training examples. So
Correct. Yeah.
But you don't know whether they are also valid for all possible programs that you might encounter in the future. So the prover may or may not be able to prove it. And there are two possibilities. One is that the rule may actually be invalid for some other unseen programs. In that case, you have to drop it. In other cases, it might be valid, but the prover is weaker. You cannot prove it. You have to drop it. So, but you can see that it's not like all the learned rules are dropped. That would be really bad. So in this case, we're happy because quite a few of them were proved. They were added, right? What is the alternative of coming up with these rules? Without our tool, you'd have to ask a domain expert to sit down and try to, paper and pencil, try to come up with these rules, right? So in that sense, we're happy with the result here.
I see. Got it. Okay. Are there any other questions from the audience?
So I have a question. So do you have a sense of how SciGuess can be, or synthesis in general, can be used to solve the problem of quantification of the amount of information leaked, like what you were suggesting at the end?
Yes. Let me go to here. So this slide really shows, the quantification. One way of looking at it is, you build a truth table, you start counting the number of ones here in the first half and the second half. So this fundamentally is a model counting problem. So there are people who are working on model counting SAT solvers, SMT solvers, with various kind of constraints. If you do that, then you could quantify, right? You get a piece of Java code or C code. You say certain inputs are random, and then you try to quantify if you have leakage. So there has been quite a few exciting works recently along that line, and both on the solver side and on applying the solver for actually quantifying timing side channel leaks and other type of side channel leaks.
I see. I mean, I just thought like model counting is hard on its own. So
it is. So the difference between the analyzer we have is we actually avoided model counting. We want to have a sound but fast analyzer. So when we cannot resolve a certain variable, we would say unknown, right? In that case, you might want to apply model counting to further refine the decision. So we actually have a CAF paper 2-3 years ago that is combining this type inference together with model counting. You run a fast type inference, and then for the unresolved nodes, you run the model counting.
All right. Thank you, Chao, once again for a very interesting talk.
Thanks for the invitation.
Yeah, thank you. And so let's move back to